Welcome to Chapter 1 of my book, Essential Mathematics for Quantum Computing, Superposition with Euclid. So to start, we're going to look at something very simple, Euclidean vectors. And usually they're three-dimensional, and we won't even need that. We'll just need two dimensions. And we'll define them to have a direction, the way that the arrow points, and then a length or magnitude. Now, with Euclidean vectors, they are equal if they are pointing in the same way and their magnitude is the same. So these three vectors here, the green, the red, and the blue, are all equal when it comes to Euclidean vectors. Now, let's dig a little bit deeper. We can take vectors and put them onto the xy plane, and their origin can be put at 0, 0, or the beginning of them. We can also show their components algebraically. So we can say vector A is equal to 3, which is 3 in the x direction, and 2, which is 2 in the y direction. Now this notation that you see here is called Brock-Het notation, or Dirac notation after Paul Dirac. And this is a ket, so you'll have a bar or pipe, then you'll have the name of the vector, and then a closed bracket here, angle bracket here. Just to kind of drive this point home, here's another vector b, and the top component of it will always be the x direction, so it's a 1 here, and the y direction will be the bottom, the y component, and that's -2. So this is geometric, and this is algebraic. Now, let's look at addition. In addition, we can do this both ways. We can do it algebraically and geometrically. For geometry, we can actually take that b vector and move it because vectors are equal if the direction and magnitude is the same. So if we move it and put the start of it at the end of A and leave the direction the same, we can then draw a vector from the start of A to B, and that is the addition geometrically of vector A and vector B. Of course, we can do this algebraically too. If you remember, our vector A is 3 and 2, which is shown here. Our vector B is 1, -2, and 3 plus 1 is 4, 2 minus 2 is 0, and this vector C here is 1, 2, 3, 4 in the x direction and 0 in the y direction. So not only can we add our vectors, we can do something called scalar multiplication. So scalar multiplication allows us to scale our vectors. And in this scenario, we'll start with our b vector, which is 1, -2, and we're going to double it. So we're going to scale it and double its magnitude. We could do that geometrically here, where we just take it and scale it, and the x component is going to still be 2, or I'm sorry, it will be 2, and the y component will be -4. We can do this algebraically. Our c vector will be equal to 2 times b, which is 2 times 1, -2. So 2 times 1 is 2, 2 times -2 is -4. So you just take the scalar, which is a number, and multiply it through the components of the vector. Okay, so now that we've learned vector addition and scalar multiplication, we can take these two things and do linear combinations. So let's start with our two vectors, A and B. And from there, I'd like to double A this time. So our vector C is going to be 2 times A, which is 2 times 3 was 6, 2 times 2 is 4. So this is our new vector C, which is a scalar multiple of A. Our vector D is also going to be 2 times B. So 2 times 1 is 2, 2 times -2 is -4. So 2, -4. Now E, a vector E, is going to be a linear combination of A and B. It is going to be a scalar multiple of two vectors, and these two vectors are going to be added together. So we can see this algebraically. 2 times 3 times 2, 2 times 1 times -2. This is 6, 4, 2, -4. We know how to do addition. So 6 and 2 is 8, and 4, -4 is 0. So we've just created a linear combination out of our two vectors, A and B, using scalar multiplication and vector addition. Now we can do this geometrically as well, as we've shown in the previous slides. We have a vector A here, that's 3 in the x direction and 2 in the y direction, and our vector B, which is 1 in the x direction and -2 in the y direction. We double vector A, and it should be 6, 4, and if we go out here, it's 6 and 4, so that's correct. We double vector B and come out with vector D, and that should be 2, -4, so 2, -4, so geometrically that makes sense. And now we want to take vector E and basically take this one here and add this one, and we know that we can just move that over there. And when we do that, it would come right to here and give us vector E, and that's 8, 0. And we have 8 in the x direction and 0 in the y direction. So we can see that we can now do a linear combination using vector addition and scalar multiplication, and we can do it both geometrically and algebraically. Okay, now that we have a linear combination down, let's talk about a quantum bit or a qubit. And let's talk about its physical representation. So to represent a quantum bit, we need to have a two-level quantum system. Now, there's a number of different quantum systems we could use. I just have two examples here. One could be the polarization of light. We could say that vertically polarized light would be a 1, and if it was a horizontal polarized light, it would be a 0. And you have sunglasses that have polarizers on them, and we could actually use those to create qubits. Additionally, we could also use electrons. So electrons have a property called spin, and when we go to measure an electron, if it has a spin up, we could say that that's a 1, and when it has a spin down, we could say that is 0. So these are two physical representations that we could use for a qubit. Now, logically, qubits are represented by vectors, and the way that we defined 0 and 1 is that the 0 vector is defined as 1 in the x direction and 0 in the y direction. And a 1 state, or 1 vector, is 0 in the x and 1 in the y. So these are the canonical definitions of 0 and 1 for a qubit algebraically. So physicists love Greek letters, and you may or may not be familiar with them. If you're going to get into quantum computing, you're going to have to get used to them. And so I wanted to introduce some of them here. This is the Greek letter psi, and it's usually used to represent the state of a qubit. It comes from Schrodinger's equation. If you are familiar with quantum mechanics at all, of course you don't have to be for this book, but that's where it comes from. And then these are the two Greek letters, alpha and beta, and we're going to use them to represent numbers or scalars that we've talked about before. So now we get to define superposition mathematically, which is the only way that matters. We know what a linear combination is because we've done that on the previous slides. If we take each component of this linear combination and say that this vector is psi, which is the state of a qubit, and then we take that scalar 2 and we replace it with alpha, just a variable. We're going to take A and replace it with our 0 vector. We'll take 2 here and replace it with beta. And then our B vector will replace with a 1. And this right here is a linear combination of 0 vector and the 1 vector, the 0 state and the 1 state. And this is what superposition is, logically. And now you know what that is. And there's also a little bit more that you get when you understand linear combinations with vectors. Measurement. So when we have a state of a qubit defined as a linear combination of the 0 and the 1 state, or 0 and 1 vectors, the probability of measuring a 0 is alpha squared, and the probability of measuring a 1 is beta squared. I'm cheating a little bit here because it's actually the absolute value squared, but I wanted to try to keep things simple. We're going to assume that these are just positive real numbers right now. Um, but yeah, or just real numbers since they're squared. But they can be complex. Now, this is a classic state here where we have psi, the qubit, is equal to 1 over root 2 times 0 plus 1 over root 2 times the 1 state. And the question I usually ask is, if I go to measure this particular qubit, what is the probability that I will get a 0? And if you want to pause the video real quick and do that, that'd be great. And the actual answer is that when I multiply this by 2 or square it, 1 over root 2 times 1 over root 2 is 1/2. So the probability of me measuring a 0 is actually 50%, or 1/2. And then the same goes for 1, it's 1/2. Or you could also just say probabilities have to add up to 1, and if you have a 50% here for 0 and your only other choice is a 1, then it also has to be 50%. Thank you for tuning in for chapter 1. It's been great explaining this to you. I'll see you on the next video.